5.2, definite integrals. Definite integrals and areas. If f is a continuous non-negative function on the interval a to b, divide the interval a to b into n subintervals of equal width by first taking b minus a, dividing it by however many subintervals you need, and that will give you the change in the x values. Then you choose sample x points in these subintervals, and then you add them all together by finding their areas, right? So here we have some distance from a to b. If we want each subinterval to be exactly the same, then we would take b minus a, divide by however many subintervals we want. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we took that and divided it by 15, and that gave us some change in x, which is the space for our base. Right, so each one of these rectangles has a base of whatever this number was. Now to find the height of that rectangle, right, we chose an x value within that subinterval. So either it was one of the endpoints, it was one of the midpoints, and we plugged it into our function. That gave us the height, right? So this is the x value within the subinterval, and this is the length of the subinterval. We find the area of that, then we add up all those areas, and that gave us the sum. So the approximate area under the curve for a function from a to b is called the Riemann sum. Okay, and it is represented by this summation. That's two n's. My letters got stuck together. Okay, so this means that we are adding areas of n number of rectangles. Alright, because you're taking the height and you're multiplying it by the base. Okay, so to find the exact area under a curve, we would take the limit of this sum as n approaches infinity. So remember, n is the number of triangles. So if the number of triangles goes, rectangles. If the number of rectangles gets as big as infinity, right? So we have an infinite number of rectangles, then we'll have the actual area under the curve. Okay? So the way that we write that in integral notation is this limit piece becomes our integration. This base piece is our function. The height piece is our dx. Alright, so let's look at some more information when it comes to Riemann sums and intervals. So if f of x has both positive and negative values on the interval a to b, then the integral of f of x from a to b can be interpreted as the difference in the areas that lie above the x-axis and the areas that lie below the x-axis. Okay, so the area up here would all be positive areas. The area down here would be negative areas. So you take the area above the x-axis, all those areas, and subtract from it the areas below the x-axis on the interval from a to b. So let's look at some examples. So we want to evaluate each integral by interpreting each in terms of areas. So this first integral has the function x minus 3 absolute value, from the interval -3 to 5. So if we look at this, we're looking from -3 to 5, which is here. Okay, so all of those areas are above my x-axis. So all of these are positive, so we'll just add them all together. So since they are perfect triangles, we can use the area of a triangle to help us figure this out. So the integral from 3 to 5 of the absolute value of x minus 3 dx is equal to 1/2 base times height of this triangle, 6 times 6, plus 1/2 base times height of the second triangle, which is 2 times 2, which gives us 18 plus 2, which is 20. Now for our second example, we want from the intervals from 0 to 3. So here's 0, and here's 3. So if we look at this line, part of this line is below the x-axis, part of it is above. So this is going to be a negative area, and this is going to be a positive area. So if we label, again, we have perfect triangles. So the integral from 0 to 3 of x minus 1 dx is equal to -1/2 base times height, 1 times 1, plus 1/2 base times height, which is 2 times 2. So this first area is negative because, again, it was below the x-axis. So we have -1/2 plus 2, so 1 1/2. Now this last piece, this last example, wants us to integrate from 0 to 1 for the function square root of the quantity 1 minus x squared dx. So from 0 to 1. So we want this area in here. So this equation is an equation of a circle with a radius of 1, which is why I know that this point over here is when x is 1. So to fill this out, we're looking for the integral from 0 to 1 of the square root of the quantity 1 minus x squared dx. And since this is only a quarter of the circle, right, this is a semicircle that's split in half, so we're going to take 1/4 of the area of a circle, which we know is pi r squared. And my r in this case is 1. Oops, this is 1/4, not 1/2. So we have 1/4 times pi times 1, which is just pi over 4. So on page 3, we have an example where it tells us the areas under the curve for given intervals, right? So from 0 to 1, the area is 2. From 1 to 4, no, yep. So from 1 to 4, the area is 6. From 4 to 6, the area is 3. And from 6 to 8, the area is 7. So we're going to use those areas to help us figure out the areas from A through F. So this area down here is going to be negative because it's underneath the x-axis. So all these areas up here are going to be positive. That one area underneath the x-axis will be negative. So if we want the area of g of x from 0 to 4, so from 0 to 4, that means we want the area from 0 to 1 of g of x dx plus the area from 1 to 4 g of x dx, which we know from 0 to 1 is 2, from 1 to 4 is 6, so the area is 8. For B, we want the area from 4 to 6, which we have from 4 to 6, the area is 3, but because it's below the x-axis, we know it's actually going to be negative 3. For C, we want the area from 4 to 8. So from 4 to 8, we have the area from 4 to 6, and we have the area from 6 to 8. So we're going to split this. So from 4 to 6, g of x dx plus 6 to 8, g of x dx. So from 4 to 6, we know we have negative 3, and from 6 to 8, we have 7, so our area is 4. Okay, so for D, we want the area from 4 to 1. So not from 1 to 4, from 4 to 1. So we're actually going to be working backwards. So from 1 to 4, the area is 6. So to go backwards, we're actually going to take the opposite. So this actually means we want the opposite of the area from 1 to 4, g of x dx. So the opposite of the area from 1 to 4 would give me negative 6, right? The opposite of 6, which is negative 6. Okay. So E and F, you can try on your own, thinking about how those intervals are split up. So from 0 to 8, right, we have 1, 2, 3, 4 different intervals that we would have to account for to get from 0 to 8. And then from 6 to 4, we have the area from 4 to 6. So from 6 to 4, we would need to do the opposite, similar to what we did in part D. So try those two on your own. And let's move on to the next page. So properties of definite integrals. The first property, if I'm looking for the integral from a to b of c dx, where c is a constant. So the integral of a constant, the definite integral of a constant, is you take the constant and you multiply it by b minus a. Now our second property is that if I'm looking for the integral from b to a, right? So remember when we're looking at intervals a to b where a is smaller than b. So if I'm looking at an integral from b to a where b is bigger than a, then what I'm actually doing is taking the opposite, or negating, the area from a to b. So similar to what we did in part D on the previous page and part F on the previous page. Right, so you're going to take the opposite of that area to get you the integral from b to a. The third property, if I'm looking at an integral from a to itself for any function, that area is 0. The area taken to get from one point to itself is 0. The next property, if I'm looking at the integral from a to b of k f of x dx, where k is a constant, then I can pull the k out to the front of my integral sign and find the definite integral from a to b of the function and then multiply by k. The next property, if I'm looking at the integral from a to b of one function plus or minus another function, then I can split that integral so that it's the integral of the first function plus or minus the integral of the second function. So very similar to what we did a little bit in A on the previous page, right? We split our integral and added the two integrals. And if I have, my last property is, if I have an integral from a to b of one function plus b to c of that same function. So on a number line, if this is a, this is b, and this is c, if I'm looking for the integral from here to here plus the integral from here to here, then what I'm really looking for is the integral from a to c, right, the whole line. So let's use those properties down below. So A asks us to find the integral from -2 to 5 of f of x plus g of x. So because these two functions are separated by a plus sign, I can rewrite this as the integral from -2 to 5 of f of x dx plus the integral from -2 to 5 of g of x dx. And the integral from -2 to 5 of f of x dx we know is 12, plus the integral from -2 to 5 of g of x dx is 4. So the total area is 16. For b, we want the integral from 5 to 1. We already know 5 is bigger than 1, so we're going to be finding the opposite here. So that'll be the opposite of the integral from 1 to 5 of f of x dx. The integral from 1 to 5 of f of x dx is 8, so we're looking for the opposite of 8, which is -8. Here, for c, we want the integral from -2 to 5 of g of x plus 3. So 3 is not a function, but these are separated by plus, right? So I can still separate these two into two separate integrals. So I can have -2 to 5 of g of x dx plus the integral from -2 to 5 of 3 dx. So we know the integral from -2 to 5 of g of x dx is 4. And we're going to add to that the integral from -2 to 5 of 3. So 3 is a constant. So if we look at our first property, we know that the integral of a constant from a to b is just the constant times b minus a. So we're going to take 3 times my b, which is 5, minus my a, which was -2. So that gives us 4 plus 21, which is 25. Let's do these last two. So for D, we have the integral from -2 to 5 of 3 times g of x dx. Here we have a number times a function. this is a constant that we can pull out. So this is really equal to 3 times the integral from -2 to 5 of g of x dx. So 3 times the integral from -2 to 5 of g of x dx is 4. So this is equal to 12. Right. In our last problem, we want the integral from -2 to 1 of f of x dx. So if we look at what we have up here, we do not have an integral from -2 to 1. We do have an integral from -2 to 5, and we have an integral from 1 to 5 of f of x dx. So how are we going to get an integral from -2 to 1 is now the question. So to get from -2 to 1, we know that we have -2 to 5. So we can at least write that we want an integral from -2 to 5 f of x dx. Now, if we look at our very last property, right, this is basically saying that we have a to b, we want to add b to c, and then in our final answer we want to have an integral from a to c. So our final answer, we want an integral from -2 to 1. So the only integral that we have up here that includes a 1 and is f of x is from 1 to 5. So in order to add this, we're going to need to flip it so that the 5 is on the bottom. So we want to add the integral from 5 to 1 of f of x dx. Because now we have the integral from -2 to 5 plus the integral from 5 to 1 should give us the integral from -2 to 1. So because we flipped this second integral and our bottom number is bigger than our top, we know that this is going to need to be a negative integral, an opposite integral. So we have the integral from -2 to 5 of f of x dx. And since this is going to be an opposite, we're going to subtract the integral from 1 to 5 of f of x dx. And that'll give us 12 minus 8, which is equal to 4. Now this last page is how to find definite integrals on your calculator. This is one of the 4 calculator procedures you will know how to do for the AP Calculus exam. So if we want to find the value of the integral from -3 to 2 of the function -x cubed minus x squared plus 6x dx on the calculator, so you want to select math, and then we want to go all the way down until we see function integral. That's what the FNINT stands for. So we want function integral, okay? And then what you're going to put in, depending on what calculator you have, right? I have a TI-84, but if you have a TI-83, you'll type in this. But for a TI-84, since we're looking for from -3 to 2, and then our function is -x cubed minus x squared plus 6x. And all of our variables are in terms of x, so we want dx. And when we press enter, we should get negative 10.41666 repeated. So this is how you would find the definite integral on a calculator. I'm going to go through what it looks like on a TA83 as well, so that for those of you who have that calculator, you can see what the input looks like. Okay. So I'm still on a TI-84, but I've changed my screen so that it mimics the screen of a TI-83. So again, we're going to go to math. We're going to go down until we see function integral. And we want the function integral. We're going to first write the function. So we want the function is negative x cubed minus x squared plus 6x. So that's our function. And we're going to put a comma because we want this to be in terms of x, right? All of our variables are x, so we want this to be in terms of x. And then we want our interval to be from negative 3 to 2. So we have our function, the variable in which our function is in terms of, and then our interval starting from the bottom of our integral to the top of our integral. And we press enter, and that'll give us negative 10.416 repeating. So tomorrow we will continue working on definite integrals. If you have any questions on the notes, you can ask them then. And you can now work on the full problem set because you have all of the information.